Welcome to one more class. So today's topic is a paper of Terence Tao, a very recent paper of Terence Tao called Almost All Orbits of the Collatz map. Attain almost bounded values. So this is a paper of Tao from 2019. Really from the end of 2019, I think it was uploaded on arXiv in September or something like that. And for those who don't know who Terence Tao is, he's a mathematician from UCLA, and it's, I think, one of the top mathematicians still alive today, and it's you can say that he's a genius of some sorts. And what is custom about his papers is that usually the proofs are very technical and long. So this is a 50 pages paper. So probably there will be part 2 and part 3 and maybe even part 4 of this class about this paper. So in this first class, what I want to do is just to recall some background about probability theory that we'll be using, and then state the main results, and after that I will state a proposition that implies these main results, and I will prove that, and then it will remain to prove this proposition, and then the following classes will prove this proposition. So basically his proof is based about a series of reductions. So start reducing the main result, reducing to certain propositions, and then the next proposition reduces to a certain other one, and so on, until we get to the very core of his argument, and that's it's going to be maybe just one class to prove this the very core of his result. Maybe we'll take a full class. So what I want to do today is just to first recall the notions about probability that we'll be using during these lectures. So prepare yourselves. We are entering in a journey to a very different land from before. So in the previous lecture, it started to become very technical, and in this one, we get to the peak of the technicalities, let's say, but still is a very nice result. Okay, so let me start with notions of probability. So if you didn't take a probability class during your master's or a PhD, whatever, hopefully all the things you need will be in this review now. Okay, so we start with a very basic thing. Which is definition of a random variable. So just to recall, so we start from the very basic things, but we see we progress very fast. So short RV, which I will often use, so it's just a function x from some space to some measurable measure space to some other measure space, and usually here, so usually the range of this function will either be like the reals or certain Rn, or maybe the integers or integers in some z to the d, or maybe the positive integers, or maybe some kind of a subset R of the integers. So it could be all those things. Okay. So that's usually the case. You can define a random variable for arbitrary measure spaces here, but that's not what we're going to be using. So an omega here is just a probability space. Yeah, and this probability space comes with a measure, which we'll call P like this, which allows you to measure things, and this is also called the event space. And this probability is associated with x. So whenever I say a random variable, it means that there is an implicit probability and an implicit space that comes with this random variable x. And x is just x is just a measurable function, in the sense that inverse the pre-image of a measurable set in K is measurable for P. Okay, so that's a random variable. So we can say, for instance, if S is a subset of K, we can say what's the probability that X belongs to S. And that will be, by definition, there's a probability in this space here of the set. So as a measure, it will be just the set of the omegas in omega, such that X of omega belongs to S. Okay, which for short is just the probability of X minus 1 of S. Okay? So that would be my notation, probability of X belonging to S. Okay, so you also will say that two random, so if you have X and Y, two random, so two RVs, let's say, two random variables. You have two random variables, then let's say both with the same range space K, then you say then you can say that X is equally distributed as Y, so they are identically distributed. That's the notion. So identically distributed if the probability of X belonging to S equals the probability of Y belonging to S for every S contained in K. So X and Y only need to have the same range, but they don't need to have the same implicit probability space. As long as this is satisfied, then we say that they are identically distributed. Okay. So as a remark, so usually we say that X is continuous. So X is continuous if its range, if its range is the real line, let's say. So if K is the real line, and so in that case, you can show that the probability of X belonging to a set is just the integral with this function here, with this measure here, where the f of x is the derivative in the measure theoretical sense of the function f of x equals the probability that x is less or equal than x. Okay. So usually we have this representation. If x is discrete, that is when k is, let's say, a subset of zd, let's say a subset of the integers, for instance, or it could be anything. So let's say k is discrete. Then the probability of x belonging to a set S is nothing but just the sum from the S belonging to that set of the probability of x equals S. Okay, and we'll be dealing with both cases. We'll be dealing with probability measures that they are discrete and continuous in this lectures. Okay. Okay, just a quick test. Okay. So another thing to recall is the conditional, let's call it conditional probability. Yes. So what's the conditional probability? Well, if I give you if x and y are random variables, then the probability of x belonging to, let's say, S1, conditioned to the fact that y belongs to S2, is defined as, well, the probability of, let me define in a very rigorous sense, which is the omega, such that x is in S1 and that y is in S2, divided by the probability of the omega, such that y of omega belongs to S2. So in another way, you could just say that that's the probability of x in S1 and x in S2 and y in S2, divided by the probability of y in S2. Okay, that's the conditional probability. If you have a function, let's say, technical problem. So that's the conditional probability. If you have a function, let's say f from k1 to k2, you could define a new random variable, which would be, so if x is a random variable, you can define the random variable f of x, okay, which is just a composition with, in the usual sense, the composition of, so that would be just f composed with x. which makes sense because x is mapping into k1. So let's say that suppose that x is mapping omega to k1. Then you can define this new random variable, which would be just a function mapping from omega to k2. Okay. Erase this thing here. Okay, so you can do that. You can also define expectation. So what's the expectation of a random variable, which I usually denote like this? Well, it's just by definition, it's just integrate the function x with the probability measure over the space omega. Which would be equal, if x is continuous, that would be equal to just integrating x df of x on the real line. So this is if x is continuous, or also be equal to just the sum of let's say k belonging to k of k, then the probability that x equals k. This is in the case that if x is discrete. Okay. So these are the things we really need. So you define condition probability here for two random variables, but there is a simpler way that we'll define it in a moment. It's by events. So the word event here will be saved for meaning, so an event is simply just a subset, let's say omega prime of omega. Okay, just so you're giving. I mean, there is an implicit random variable that was given here, and this is the probability space, and just taking a subset of that is an event. So, for instance, an event could be just the set that x is, let's say, suppose that so that x belongs to a certain set S, and I would denote like this, like by a statement, let's say. So another event could be, so an example that we will see often now is that, so suppose you have C, the Collatz map. So C is the Collatz map. And you define C mean of n to be the minimum in the orbit. So n, C of n, C squared of n, dot, dot. Okay? So a typical event that we'll be exploring here is something like C max of x finite and what else? X is prime, let's say. Maybe prime will not show up. It's just a artificial example here, where x is just where x is a, let's say, is a z plus valued random variable. So x takes values into random, into positive integers, so you could say, is this finite, and this is a prime. So that would be an event in the probability space, because these will be implicitly the collection of the omegas in the probability space omega, such that these conditions hold. But again, so the idea is to imagine x as to be a kind of a tryout, is just trying to take integers, positive integers, for instance, according to the probability distribution of x, and for each of those integers you're, let's say, picking out of a bag according to this probability measure. You say yes if this event happens. Okay, so that's the kind of way you should interpret an event. Again, I'm not here to teach you about probability, but I'm just reviewing the concepts. Okay, so for instance, if an event E1 implies an event E2, then the probability of E1 is less or equal than a probability over 2. Yes, E2 is more likely to happen because, well, whenever E1 happens, E2 also happens. Okay, so, and these kind of implications are always understood that there is implicit probability space, and it's the same probability space for the both events to make sense. Okay, and the probability of an event is just a measure with this probability. So if E is an event, then just to be completely rigorous, this should be just the probability of the set which this event is defined. Okay. Erase the part. So now I can define, well, I define conditional probability for random variables. You can also define conditional probability for events, which is what's the probability of event 1 happening given that event 2 happens, and that's by definition just well, the way I defined before is just the probability of event 1 happening and event 2 happening simultaneously divided by the probability of event 2. Okay? Yes. So, in particular, if you have En is a partition of the probability space, in the sense that for every, let's say you have a random variable x, which is just drawing integers according to the distribution of x. So just taking those integers, and you know that either one of these things, and exactly one of these events, En, happen. So that would represent a partition of the space. So in particular, the probability of an event E happening is equal to the sum of the probability of that En happens and the conditional probability of E happening given that En happens. Okay. So this is a nice formula to keep in mind. So basically, you're saying a probability of E is just a convex combination of the conditional probabilities. And the nice thing is that if you can, and we will do that often, if you can use it, you can give a bound for these quantities here, which is uniformly depending on some parameter, then you can recover a bound for the event E. What I'm saying is if you can make a bound for this, which is independent of n, then you can make a bound for this. Okay, so that's but this allows you to, if you have an event which you don't know how to work with, then you can maybe work with these events which have more structure because you're assuming that En is happening, and then if you can give a uniform bound to this, you then give a uniform bound to this P, and we'll be doing that a lot here. Okay. Okay, maybe I can find this later. So there is also conditional expectation, but maybe I will define conditional expectation when I actually use it. It will be in the other classes, not this one. But the final important thing is the total variation. So total variation is a way of measuring let's say the correlation between two given random variables. So how close they are. Okay. So if x and y are, let's say, k-valued random variables, so they don't need to have the same implicit probability space, they just need to have the same range, or at least the range of or one and the other is contained, both ranges is contained in a larger measure theoretical space. So that would be the generalization for this. But k, again, will always be the integers or the real numbers or the subset of these things. So the total variation between x and y is just the summation of... And so I will define in this way, because we're only using for k discrete. So we'll define like this. But you can define in general. Okay, so I will only do total variation when the space is discrete. So we'll define like this. So when k is discrete, so it's just okay. So you're just measuring the probability here. So note that this guy is not equal to this guy in the implicit way, and we'll stop saying this for now on, okay? Because this will be always implicit. And what you can show problem, not hard to show, it's a simple exercise, that the total variation of x and y is greater or equal and less or equal than twice, so it's comparable to the supremum over all subsets of k of the probability that x belongs to S minus the probability of y belongs to S. Okay. So what you're saying is that the total variation is comparable to the probability the difference of the set where these random variables most disagree. Okay. So in particular, if you have two random variables, two functions, let's say, f, so the probability of this belonging to a set will be greater or equal than the probability of this belonging to the same set minus the total variation of x and y. And this is for every function f from k1 to k2. Okay. okay, and yeah, K1 and two discrete probabilities, two discrete spaces. Okay, so this is a way of measuring. Suppose I want to estimate the probability measure of f of x belonging to a certain set. Then what I do is I just measure y, and I know that y is pretty close to x, so this number here should be small. So that's a way of creating bounds for this guy and this guy. Okay, so I think we can go to the main results now. So let's go to the main results of Tao's paper. We still have a bunch of definitions to do, so we'll probably erase the whole board now. So making this paper available to, let's say, master's students is very challenging. And hopefully I will be able to do it, but maybe I'll fail. I don't know, we will see. Okay, and also, completing what I just said, Tao has a very particular way of writing papers. That he's been writing papers like this for a long time, and they are usually very technical, so it's also very hard to write them. But he has this particular style that you have to get used to in order to understand the stuff he does. So if you try to read the paper, it can be very, very challenging. It is for me. So, okay, so before I state the main results, I need to do a bunch of definitions, and then I can state the main results. So the first definition, so we had the Collatz map. So we call that, maybe we should recall, C of n is just n over 2 if n is even, and 3n plus 1 over 2 if n is odd. But we also had this speed up Collatz map, which is also called the Syracuse map, which we denote by S. So S of n, so S will be a map from the odd integers to the odd integers. So in my notation for odd integers is just the word odd. So odd denotes the word, English word for odd integers, but also the set itself. Okay, defined in such a way that S of n equals 3n plus 1 divided by 2 to the new 2 of n. A new 2 of n, maybe a new 2 of n already defined in Crandall's talk, and also S already defined in Crandall's paper when it was presenting Crandall's paper, which I think it was second or third lecture, I don't know. Nu of 2 here is just the largest nu 2 of n is just the largest a greater or equal than 0, such that 2 to the a divides 3n plus 1. So what you do is basically you take n and you multiply by 3n plus 1, you do 3n plus 1, and you just take all the powers of 2 in the prime factorization of 3n plus 1. And that's what you do. So if it's odd, then 3n plus 1 is going to be even, so this guy is going to be at least greater or equal than 1. So this will be a map from odd to odd, and then the Collatz map, the Collatz conjecture, will be equivalent of saying that S of 1 is 1, but that's obvious, and that any other number, once you iterate indefinitely, it eventually gets to 1, it gets stuck in there, okay? So that would be the Collatz conjecture. So the Collatz, let me write here. Collatz conjecture would be equivalent of saying that for all n greater than equal than, let's say, 1, there is a j greater than equal than 1 with sj of n equals 1, and once it becomes 1, it will stay there forever, okay? Because this is the speed up version. Okay. So, okay, so that's the one thing. The second thing will be I will define for an x which will be real, so r plus is just positive integers. So this is just 0 infinity. So for any r, for any x, I will define this function here, which will be the first k such that sk of n is less or equal than x. So I'm taking the first guy such that once I'm iterating s, it becomes less or equal than x. But if that guy doesn't exist, I just put plus infinity. Okay? So this is what Tao calls the first passage time. So it's the first time it gets below a certain number x. Okay, so that's the moment, let's say, that the time representing the k. And then from this we can define the first passage, which he uses the word pass, but I will just use p here. So pass of n will be the guy that gets, the first guy that gets below x, so it will be s of t of x of n, if tx of n is finite. If it's not finite, then I will just put 1, okay, otherwise. So this is kind of artificial, but this 1 here doesn't have much sense. So it's artificial, but useful. And the main thing is just that I want this function to be well defined for every integer. I don't want to separate things in cases, and it will work anyway. Okay, I will define, so orbit, I will just write the word orbit, which is just to set n as n, s squared of n. And I will also define s min of n, which will be just the minimum number in the orbit. Okay, so just take the minimum number in the orbit. So the Collatz conjecture can be restated as for all n greater than equal than 1, s min of n equals 1. So that will be equivalent to the Collatz conjecture. Okay, what else? So Tao wants to prove a probability result. He wants to show that for almost all integers a certain thing happens. So this almost all has a notion behind it, an implicit notion, which is according to a certain density distribution, a certain probability distribution, if you wish. Usually that word almost all is reserved for the natural distribution, which is just counting, which means this counting function. But he's going to use the log distribution. So So for that I need a definition. So so let R be a subset of Z plus. So we let, and this is customary to use this kind of notation that we use now. Log of R, this would be a random variable, is a, so let me write the range, is a R valued. So it has values on the subset R, random variable. So that it has an implicit probability space, which could be anything, it's just a random variable which is R valued, but you will say what's the probability distribution. So the probability distribution log R belonging to a certain subset A will be just the sum of the n's in A intersection R of 1 over n divided by the sum of the n's in R, 1 over n. Okay. So he's using what's called the log distribution. So if it was just using the counting function, I would just put here 1. So we're just counting the numbers of guys in A intersection R divided by the number of guys in R. That would be the natural distribution. He's using the log distribution, okay? So we'll use the word log distribution, log density, almost all in the log sense to say that I'm using, instead of a counting function for the integers, I'm using the log distribution. Okay. So the main theorem of his paper, which is not exactly way as he stated, but it would derive the ways as he stated from theorem 22. So in my notes, is theorem 22 is the following. Yes, for all delta, let's say from 0, 1, from the interval 0, 1, there exists a C delta, and this can even be made quantitative, or quantitatively, I don't know. You can see I still have to improve my English. Such that, so there is a delta positive such that the probability of S mean of log of the set 1x is less or equal than C delta is greater or equal than 1 minus delta. For all x greater or equal than 1 sufficiently large. So maybe she should say for x greater or equal than 1 sufficiently large. So that means that there is another constant, let's say C prime of delta implicit here, that when x is greater or equal than this C prime of delta, this inequality holds again. So that's the result, okay? So what the result is saying, so before I go ahead and start to work towards proving this thing, what is saying? What is this saying? So this is saying the following, so maybe I should put here as an observation. So maybe before, what I would like to say, so what I would like to say is something of the sorts of, well, I'm counting, so when I want to say something like, I'm counting the integers, positive integers, less or equal than x, such that S mean of n is So I want it to be 1 for all n. That's the Collatz conjecture. But maybe the only thing I can say is that this thing is bounded. So I'm counting, like say, when this is less or equal than a C delta. Okay, so what I'm saying is that, well, it gets, you start with an integer, then it gets to, so it started iterating, it can go very high, but at some point it gets to a very low number, comparably, to n, which is a C delta. So I want to count this thing and divide this by x. Okay, so that would be the one nice thing to do. Well, because for instance, we saw in the Terence paper that he showed that S mean of n is less than n for almost every integer. So if I put, instead of C delta here, I put the n, then I know from the lecture about the paper of Terence that this would converge to 1 when x goes to infinity. But Tao wants to put the bounded here, so a constant, so that's it. So that's why the title is almost bounded. There is the word almost bounded in there. So that's what I would like to do. But I'm not able to do that with the natural. So that would be the natural counting function, counting measure. So I can't do that. So what he is doing instead is the following. He's defining a density, let's say. For the moment, let me define it like this, which will be the n's less or equal than x in odd. Oh, I didn't explain what this is. This is just the integers from 1 to x that are odd. So that's why I'm putting odd here. And S min of n less or equal than some constant C delta. And I'm doing 1 over n and dividing this whole thing just by this. Okay, let me do this density, which was the same as before, but instead of counting integers, it's counting 1 over n. Okay, so what he's saying is that this thing is greater or equal than 1 over delta if x is large. That's what he's saying, that for every delta, so for every quantity here as close as you want to 1, I can find a constant here such that the density of the integers that eventually get below that constant is greater or equal than 1 minus delta. So in particular, he's showing that the limit inf of this density in x is greater or equal than 1 minus delta. So you can do that as well. Yeah, so that's what it's showing. Okay. So that's the exact statement here. But in here, I'm just phrasing it in terms of probability distributions and so on. Because I'm taking the log, so I'm taking this distribution and only numbers from 1 to x, great. I'm taking the minimum, which is this guy here. I'm asking if it's less or equal than C delta, computing the probability of this event, which will be exactly this. So this is phrased in just probabilistic terms. Okay, so let me make some remarks about what we had before and why is this largely improving the previous results. So we did the paper of Crandall. In the paper of Crandall, we showed that S min of n was less than n for almost all integers. And this was in a natural sense, which is just using the counting measure. So in a way, what so in a way, what Tao is doing is much better because he's putting here a bounded constant, and then over this there was an improvement by Alaouche, which showed that, and this is 0.869, so this holds again for almost all integers. And there was again another improvement by Korek, which showed, which reduced this to 0.79, 24, etc. And this number here is actually, this guy here is just a half of the log base 2 of 3. And what Tao is doing is replacing these functions here that grow by anything that can grow. So the corollary of Tao's result, let's say corollary 23, which is the following: let f, to take any function such that, and this is the way he phrases. Okay, so a function from the integers to the real line that goes to infinity when n becomes larger. Then So one thing you could do is you could try to improve these results as before, trying to reduce its exponent. What Tao does, he just completely destroys everything here and proves something much better. So for almost, so then S min of n will be less than Fn for almost all integers. Okay, so you could replace this n to anything, 0.00001, the result will be true. You could put anything. You could put Fn, it could be log of log of log of log of log of n. It could be something growing very slowly. And still, almost all guys satisfies this. Well, if the Collatz conjecture is true, this S min should be equal 1 for every n. So in a sense, we should be able to do that, and it does. The only catch here is that in the log, let me see the reader right here, log density sense, which is that the sum of 1 over n of the n's less or equal than x, such that S min of n is less than Fn. You divide this by just 1 over n less or equal than x. That converges to 1 as x converges to infinity. Okay, that's what it's saying. So if you replace this thing by the counting measure, it will be exactly as the almost all that they used before, but in here he's using in the log sense. Okay. So we are 40 minutes in. So let me just prove how can we show corollary 23 from theorem 22. It's a pretty simple argument. And then, so this is a statement for the Syracuse or the speed-up Collatz map S, but you could also make a similar statement for the Collatz map, and we'll put that as an exercise actually. So let me just erase this part here. Okay. So let me prove that theorem 22 implies corollary 23. Okay. So so let me define density tilde as just, well, exactly as it be defined here. Oh, this is supposed to be n odd because S only exists over the odd ends. Okay. So let me define this thing here as density x tilde. So this thing doesn't depend on delta, like the stuff that was written here that I erased. It's just depending on x. So let me define this density like this, and let me so let delta be a number between 0 and 1, and what you do then you find and see delta as in the theorem 22, which I erased. So now you take some n delta greater or equal than 1 such that, well, f goes to infinity. There is, I'm showing theorem 22 proving corollary 23, so there is an f. And f goes to infinity when n is large, so therefore f of n will be greater than c delta if, let's say, n is greater or equal than n delta, for some n delta. Okay? Okay. Great. So therefore you have that the set, let's say, n odd, n delta less or equal than n less or equal than x, and that S min of n is less or equal than c delta. This set is contained in this other sets, because if it's less or equal than c delta, well, it's less or equal than f, of course. Okay. That is to say that the event that this is less than delta implies the event that this is less than fn. Okay, so I conclude that the density tilde is what? Well, the density will be just will be greater or equal than density x, where density x, maybe I should define density x here, is just a sum n less or equal than x, n odd, and S min of n less or equal than c delta. So the density x depends on delta, and this is just 1 over n less or equal than x, n odd. Okay. So what's the difference between these two? Well, if that is less or equal than so density x would be the stuff that is less or equal than fn. Okay. So what you do is you take density x, you start from n delta, so you lose a term, and then in this you you have that if this is true, if S means less or equal than C delta, then it's less or equal than Fn. So this set here, as I wrote in there, is greater or equal than this set. So I can say this, yeah, so in that set we have the inequality, but then you have to also remove the beginning. So you see that this is greater or equal, I'll leave the detail for you to fill up. And then minus, yeah, so this is me removing the first part in density tilde, and then this is me removing, putting back the beginning that's supposed to be here. So this whole thing divided by the sum of 1 over n, and let's say equal to x and odd. That's what we have. Okay, and this holds for every x greater or equal than n delta. So when I take x to infinity, I conclude that the lim inf of the density tilde of x when x goes to infinity will be greater or equal than this. But this guy here, we know by theorem 22 that if x is big, this guy is greater or equal than 1 minus delta for large x. It's a greater than 1 minus delta for large x. So we have here 1 minus delta. And when x goes to infinity, these two, the part in the numerator doesn't depend on x. And this diverges because it's the harmonic series. So this goes to infinity. So therefore this part, this whole thing goes to 0. So you just get this. The density tilde doesn't depend on delta, it's just a quantity. And also clearly that density tilde is less or equal than 1. So therefore the lim inf is greater or equal than 1 minus delta for every delta. So the lim inf is 1. So the lim inf has to be less or equal than the limit sup, which is less or equal than 1 because this is the density. Therefore the limit sup equals the lim inf. And therefore the limit exists and is equal to 1. So we conclude that the limit when x goes to infinity of density x is 1. And that's exactly what we wanted to show, which is Collatz 23. Okay? And then we'll leave as a problem to prove the same thing for the Collatz map. So let f yeah, in here, well, it doesn't make much sense if I put n not odd, because s is only fine for n odd, so I should put here odd. So this is just any function r plus such that f infinity equals infinity. That not has a way of saying that the limit when n equals to infinity is infinity. Min, where C is the Collatz map, and min is the minimal number in the orbit of n. For almost all integers. So probably I should say here for almost all odd integers, and here it's just for almost all integers, in the log sense. So in the log density sense, okay. And if you want a hint, you can see my notes, or you can just try read Tao's paper. But it's not that difficult. It just requires you to realize, and you can even see, maybe I did that already in Crandall's talk, an argument similar to the argument you need here, which is the relation between C and S. You can make a relation for these guys, and then from that relation you can deduce this thing from corollary 23. Okay, so now we are in the final part of the lecture, and this final part, what I want to do is to state a proposition, give you an idea what the proposition is talking about, and then use that proposition to prove the main result, theorem 22. And then we will finish, and then next class we will prove proposition 24, this proposition that I mentioned, assuming another thing, and so on, and proving this another thing, assuming another thing, and so on, until reduce to a thing, which is the most difficult part, and this most difficult part will require a lot of work. Okay, let me erase everything. Yeah, so before I prove a proposition, let me define the following. So nx will be a random variable, which will always be log of the set x to the alpha. So there is an implicit alpha here. There will be an implicit alpha during the rest of all the lectures, and alpha will always be a number between 1, greater than 1, but not that great, much bigger than 1. So it's a number close to 1, so an odd. So just the odd numbers from x to the alpha, where alpha is some number bigger than 1. Okay. So to be rigorous, this thing depends on alpha, okay? But alpha will be a number bigger than 1 that will be showing up frequently, and then eventually you will see that we can choose any alpha as long as alpha is very close to 1 but bigger than 1. Okay. So basically this is just a random variable which has values in this set, and it's distributed according to the log distribution. Okay, so proposition, what is proposition 24, which Tao calls stabilization of first passage. Okay, which is the following. So again, he writes in a certain specific way, and you have to get used to it. I will try to translate here to a certain way of writing that is more accessible to master's students. So I guess this is proposition 1.11 of this paper. So there is a certain epsilon greater than 0. There is a certain c greater than 0, such that first is that if 1 is less than alpha is less than 1 plus epsilon naught, then the probability of the event Tx in x alpha be finite. So this is an event because T of x is a function, well-defined function, the natural numbers, and x to the alpha is just a probability, is just a random variable which is integer valued. So this makes sense. And the probability is much less when a constant dependent of alpha, x to the minus c. And I will mention what is this notation in a moment. And if 1 is less than alpha, squared is less than this epsilon naught, then the total variation of p of x of nx to the alpha and px nx to the alpha squared is much less with constants depending on alpha only, log of x to the minus c. Okay? So this is the proposition. Okay, so let me, before I give some intuition about it, let me just do this. So we will always write it something like this. So a left is less or equal than something on the right if there exists a c, and this c depends on this lambda, this object lambda, which could be a bunch of constants or functions, etc. So it depends on lambda, such that L is less or equal than c lambda r. Okay, so L and R are positive quantities. I will also use the O notation. That would mean that whenever this term shows up, is that it means that if you take the moduli of this term is actually less or equal than a constant, which depends on lambda, times this stuff inside R. Okay, so that's the notation I'll be using. Tao is using this symbol here in Tao's paper, which is equal to this symbol here that I'm using. Okay, it's just a matter of taste. I usually use that, and I don't want to change that. Okay. So what's the intuition here? So the intuition is maybe it's better to give you the intuition of about this proposition in the end. Okay, so in the end, after I show that this implies the main result, we'll give you some intuition. Then because the intuition is based on you previously knowing certain things, and then you can have this intuition. Okay? Again, as far as I could understand the intuition. Okay, so let me prove that proposition 24 implies theorem 22. So what's theorem 22, just to recall? So theorem 22 is saying that the probability of S mean of log of 1x only over the odd. Oh, I should put odd. I put odd already here. Odd, yes, less or equal than some constant c delta is greater or equal than 1 minus delta. But another way of writing this is that if I put a b here, then this is supposed to be greater or equal than 1 minus some function that goes to 0 when b is large. That would be just another way of rephrasing it. So maybe you can do that, realize that as a problem. And what we're going to show here really is that this is O of log b to the minus c, and this is for all b greater or equal to 1. That's what we're going to show. Okay. So, okay. And that would imply, because if I take b very large, then this would be delta, and then just invert whatever appears here and put in here as a constant, and that would imply the result. Okay. So that's what we will show, and this c, you can already guess, comes from this proposition here. The constant here actually can depend on this alpha here, but you can take any alpha in this interval. So you could take, let's say, let me put even less or equal here, for instance. So you could take this guy here, for instance. So that's what we're going to prove. Okay. Yes. So first of all, let me show something. Let me show something, then I maybe can give a representation. Okay. So let me define this n tilde x variable, which will be equal to that guy here, just log. So that won't depend on alpha. Okay. So, yes. And then let me define these intervals here, ij of x, which will be, to be completely rigorous, I should put open interval here, x to the alpha to the minus j, and x to alpha to, should be, to be very clear, it should be x to 1 over alpha to the j, and something larger, which would be x to 1 over alpha to the j minus 1, and close. Okay, and alpha is just a number greater than 1 and less than the epsilon naught, so it's 1 less than alpha, let's say equal than 1 plus epsilon naught. Okay. 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 Okay, so let me define this. So what you realize is exactly what I told you before about conditional probability, is that the probability that S min of n tilde of x is less or equal to b, which is exactly what we want to measure now, will be a sum over the j's greater or equal than, I guess, 1, so it can end on x. Yeah. Of the probability that S min of n of x tilde is less or equal to b, conditional to, we are actually inside one of these intervals, times the probability, maybe I can put here, of this interval. Yeah. So to be completely rigorous, I should put here maybe times the probability of n tilde of x belonging in this thing. Okay. Okay. So I'm just using conditional probability now. But then what is this here? This thing here, well, first of all, you have to realize that these intervals here create a partition of the interval. Oh, this is supposed to be odd again. Odd here. So create a partition of the odd numbers from 1 to x. Therefore, I can use conditional probability. And actually, this thing actually ends at some point, of course. It's 1 from certain jx. Okay. But, and then the rest, the intervals are empty, which means that this probability is 0. So I could actually just summate up to infinity, but you know that there are only finitely many non-zero terms. Okay. And now comes the comment that I made before. I can bound this uniformly. If I can bound these guys here uniformly, then I could bound this. So, but what is this? This is exactly the sum from greater or equal than 1. And what is this? Well, I have log distribution, less or equal than b, and I also have to belong to this interval. So it's exactly the random variable I defined before, n. But now is probability of S min of n. And what is the x? Supposed to be the, so maybe I should define like this. Yeah. Okay, so to make much more sense. So open interval and interval here. Okay. So it's exactly the first guy that should appear, which is this guy right here. So x to the alpha to the minus j, less or equal than b, and then probability of being here. Okay. So if I can bound these guys here inside from below by 1 minus O of log B, and that O is independent of X, so it's dependent of this thing, as long as it's greater or equal than 1, which will be the case because the sum will stop whenever this is less or equal than 1, less than 1. So if I can do that, then I can just extract the uniform bound out of the summation, and this summation will be 1, so therefore you get a lower bound for this. Okay, so now the goal is to prove that the probability of S min of nx less or equal than b is greater or equal than 1 minus O of log b to some minus c, and this O doesn't depend on x for all x greater or equal to 1. Okay? So it means that there is a constant here that's not depending on x. Okay? Of course, that for the first x1 up to 100, maybe to 1,000,000, this thing here is so large that this lower bound is negative, so it doesn't mean anything. But when x gets pretty large, and when b gets very large, this starts to make sense. Okay, and that's the whole point. The whole point is for b large. Okay, so that's the goal. Okay, so now you have this probability measure here, which you don't know how to do, and what to deal with. What Tao is thinking about, and that's why he's putting this x to the alpha there, is that maybe there is a way of relating. So maybe there is a way. So maybe that maybe make here parentheses to give you the motivation for the proposition. Maybe there is a way of comparing nx with nx to the alpha. That is, this guy is distributed in here, and the very next interval would be something like x to the alpha squared, which where nx to the alpha is distributed, is valued. So you have these two intervals, they are disjoint, so maybe I should put open here. They're disjoint. So how can I relate them? Well, these are two probability distributions that have disjoint range. So if I could compute the total variation between them, it's not going to give you anything. It's just going to give you 2. That will be the total variation. Okay, which is meaningless. So what you can do is, in a way, use a function to map this variable. So the same function uses a certain function f, so finds a certain function f, such that f of nx and f of nx to the alpha are related. That means that the total variation between these two guys, these two new guys, is small. And that's what he's doing here. And this function just happens to be the first passage function. So now you're taking all these guys here. Well, he's doing the argument for x to the alpha squared. So but it's just replacing x by x to the alpha. So let me put alpha here and alpha squared here. So it'll be alpha squared and alpha cubed. Okay. Make sure that's the. Yep. Let me put alpha here and alpha squared. So you find f such that these are related in the total variation sense, meaning that the total variation small. Okay, and that's what he's doing here. And he's taking the first passage function. So the first passage function, we map any guy here for this random variable. So for any guy in the range of this random variable, that is the interval x to the alpha to the x to the alpha squared, we map to a number which is less or equal than x. And also here. So the range of these two things are now closer, let's say, because they're all numbers less or equal than x. And what happens is that they are related in the sense that the total variation of these new probability measures is small. So, and then he mentions in the paper that, well, if this map px was measured preserving somehow, then the probability of this event would be equal to the probability, or the probability of this thing belonging to a certain set would be less or equal than the probability of this thing, would be equal to the probability of well, so what he wants to do, so maybe that's a better way of doing, is that, well, the function f is p of x, this is p of x, this is p of x, okay, but then what you realize is that the s min, well, this guy here is on the orbit of n of x alpha, which means that the S min of a guy in here is less or equal than the S min of the guy in here. So the S min of px and x to the alpha is less or equal than the S min of nx. Greater or equal than the S min of this. Well, because both sides are taking the minimum of the very same orbit. It's just in here you're taking a minimum from a starting point which is not 0, and here you're taking a minimum from the starting point which is 0. Therefore, the mean here can be larger. Okay. So if this thing is less or equal than b, okay, then this thing here is less or equal than b, okay? But again, since these probability measures here are related, px, these guys are related, okay? I could say, in some way, I could make that the probability measure of S min being less or equal than b be related. So the idea here finally is that from here to deduce that the event that S min, the probability of the event that S min of x alpha is less or equal than b could be related with the probability. So the probability of this will be close to the probability of the next one. So these two numbers will be close. That is the idea. So I want you to deduce that these two numbers here are close, but I can't. I can only deduce that these two probability distributions are close. But since a bound for this thing implies a bound for the S mean of the first passage implies a bound for the S mean of the original number, I could then make an argument that these two numbers, the probability in here and the probability here, are close. Okay. So that's more or less the idea. I think I got it right. And he comments in the paper that if P of X was measure preserving, that will be even easier, because in a way, if these two things are close, then the probability distribution of this function here and the probability distribution of this thing is close. Therefore, if Px was preserving measure in some way, then the probability that this satisfies something and the probability of this thing inside that satisfies the same something would be close. That means this thing here would be close. So if Px was measure preserving, then it will be a much easier argument. And what he will prove is that Px is not measure preserving, of course, but it's close to be measure preserving in some way. And this still will allow you to prove that these two numbers are related, okay? And the point is, well, why we want these two numbers to be related? Because there is a standard probabilistic argument that you can make. Tao uses this, already used this in other papers. That whenever you prove that something like this is close, then you can make an argument for, using this conditional probability technique, proving something for this. Okay. So that's more or less the intuition. And there's the first part here is just an intuition about what happens in. So there will be an induction step that you have to make, and this is just about the base case of this induction argument. Okay. So let me write the proof, and you will maybe understand more about the intuition. So as far as I could understand, that's the idea. You want to compare these two things here, but you can't. Then you come up with a function to help you to compare these two things, and the function is the first passage, and you realize that this thing is true. So the total variation is small, and that allows you to come back and say that these two numbers here are close. Okay. Okay, so enough about my interpretation of the intuition, which could be slightly wrong or maybe totally wrong, I don't know. Let me prove the thing. So let me maybe erase everything. The proof is not long. It's actually a kind of a standard procedure, I would say. For the experts, again, for the experts that work in these kind of a probabilistic arguments every time, then this is a kind of a standard argument. Okay. So let me define the proof, or erase the thing. Let me continue the proof. Again, we want to show that the probability of S mean of n tilde of x be less or equal than b is greater or equal than 1 minus something, which is O of log of b to minus some constant c. Okay, well, where n tilde x is just log on 1x odd, and n x, just to remember you, is just log of x to the alpha odd. Okay. Okay, so let me define the event. So define the event. Okay, and then, well, this was the main result, but then we reduce it to show that we remove the tilde here, and that is true. Okay? And that is true, and then, well, the bound would now depend on alpha, but alpha could be anything less than, greater than 0, but close enough to, greater than 1, but close enough to 1. Okay? So that was my comment with the conditional probability. You can remove the tilde. So now define the event, and Tao defines it the same way. Bx is just this is Px. Okay, so this Bx is not exactly this, but what you can deduce is that Bx, well, if the S mean of this thing is less or equal than alpha, then, yeah, so B, maybe we should put here Bx of 1 over alpha, to be fair. So replace everything by 1 over alpha, so you put 1 over alpha here, and this is P of x, 1 over alpha, and nx. Well, if S mean of P of anything is less or equal than B, then S mean of this thing is less or equal than B, because it's just taking the same orbit, and the mean can be smaller or not, but it's less or equal than the same upper bound. So that would imply that that implies the event that S mean of nx is less or equal than B. Okay? So in particular, the probability we want to estimate that's a probability we want to estimate is greater or equal than the probability 1 alpha. Okay? So now we want to create a lower bound for these things, for every x, okay? And my claim, and this claim will be true because of the proposition, is that the probability of b of x to the alpha is greater or equal than the probability of bx minus O, which can depend on alpha, log of x to the minus c, for every x greater or equal to 1. And the probability of b of x 1 over alpha, so what's the probability of bx 1 over alpha? So you want to know the first time that guys in here get, oh, so this is supposed to be open here, I always forget. So Tau puts closed here, but I guess to be really rigorous to be open here. So if I put x 1 over alpha here, then I get just x 1 over alpha to x. So every guy is already born less or equal than x. Okay, so oh, sorry. Suppose if yes, so if x is less, it's supposed to be if okay, this guy's going to be less or equal than x. So if x is less or equal than b, so suppose x is less or equal than b, then b of x 1 over alpha is just, what is this, 1 over alpha, this is in x, this is finite, and S mean of px 1 over alpha of nx less or equal than b. Okay, but that is always true because well, you're taking here guys which are, after you apply the first passage, are always less or equal than x to 1 over alpha, which is less or equal than x. So all these guys here are already less or equal than x. So the min is going to be less or equal than x, but x is less or equal than b. So this is always true. So this is just, I can't ignore this part. Okay. Okay, so that's just the event that this is less than finite, which therefore the probability of x 1 over alpha, okay, which yes, the probability, but this is only for x less or equal than b, by the way. So I'm assuming x is less or equal than b. So the probability of x1 over alpha would be just 1 minus the probability that this is infinity. Okay, and that's exactly in the form of the lemma, the proposition, instead that in here I had x and x to the alpha, which will be the same as x to the 1 over alpha x. Yes, so this would be greater or equal than 1 minus O of something that depends on alpha, of course, of x to the 1 over alpha to the minus c. Okay, so where c comes from the proposition. So this was part 1 of the proposition. So this was the first inequality. So this is proposition 24. Okay, so c over alpha we just call it another c. Okay, because alpha is greater or equal than 1, so we just call it another c. Okay, so we'll just say 1 minus something that depends on alpha. So I want to increase, so I could just put alpha equals 1 if I want here, because this would be 1 over x to the c over alpha, and so if I want to increase that quantity, I increase the exponent, so I reduce alpha to 1, since alpha is greater than 1, so this is O of x to the minus c. Okay. So now you have, and this is the part that I said that is a standard technique, which is the following. So let me prove the claim. So I still have to, let me prove this claim here. Okay. So this was just an observation for the first part. Let me prove the claim, and then from the claim we will start an induction. After I prove the claim, I will do an induction argument. Okay, so how can we prove the claim? And the claim is actually not that hard to show. So let me define, for the moment, so what is the event bx alpha? So let me just rewrite it. It's just tx alpha, yeah, so nx alpha squared, finite, and S min of px alpha, nx alpha squared less or equal than b. Okay, that's the event. Well, that implies what? So that implies what? No, sorry. That is implied by what? So, what implies px alpha? Okay, so I have to, there's a typo here in my notes. Yeah, because this will be doing the larger event, so I can bound this from below. It's exactly what we want to do here. We want to bound this from below. So what implies this event? Well, I'm looking for things that get below, eventually get below x to the alpha. But if x is less than x to the alpha, therefore if I get below x, I definitely get below x to the alpha. So I can replace this by x. And well, a term here in the orbit of this guy, nx to the alpha squared, which is before the first passage below x to the alpha, which is after, sorry, is px. So if this is less or equal than b, then definitely, if this is less or equal than b, because it's implying that. So okay, so the reason why this event here implies the event b x alpha is the following, and is the following. Well, the reason is that, well, we have this inequality here, which I should actually put like this. If y is greater or equal than x. And why that is true? Because, well, this is the first time I get below x, and it's the first time I get below y. So, but since x is less or equal than y, so if I get below x, then I have to get below x after I get below y, because y is bigger. So if I get below x, then I definitely got below y before. So that's what this inequality is saying. In particular, you conclude that S min of ty of n and is less or equal than the S min of, yes, tx. Oh, sorry, it's supposed to be the first passage p, and this is supposed to be p. If y is greater or equal than x. Well, because, well, since I get to y before I get to x, that means that in the orbit of n, this number here, yn, appears before pxn, because first I get below x and then I get below, first I get below y and then I get below x. So this number here appears before than this number in the orbit of n. Therefore, I have more terms to take a minimum, so therefore the minimum is less or equal than the minimum in this part, okay? So this thing implies that this event implies Bx alpha if you take y equals x to the alpha. And then, so I made a mistake in the explanation I did in my original video, which you were just watching. So you will see something like this implying that, but the something like this that appears in a box is actually wrong. So that's the right explanation. I mean, it's likely wrong, not totally wrong. But that's the right explanation. So continuing. So therefore, the probability of p of x to the alpha is greater or equal than the probability of this event of tx and x alpha squared less than infinity and s min of px and x to the alpha squared less or equal than b. Okay. And because this event is more likely to happen, but then we have a way of splitting this thing because so what's the probability of this? So this would be I guess equal. Yes, that will be equal to the probability of this minus the probability of tx of nx to the alpha squared equals infinity. But then by the proposition which I raised, this thing is O of x to the minus c. Okay. Yes. Yeah. So probably I should. So the proposition I should remember, and also I should include a correction in the proposition. The proposition was I should put it here. The proposition was that the probability of this thing is O of x to the minus c, but this also works if I put a square here, okay? So also, so this was the first item of the proposition, but I should put more. I should put also, which I forgot, alpha square equals infinity. That is also O of x to the minus c. So that was item 1 of the proposition, and item 2 was that the total variation of the first passage of nx to the alpha and the first passage of nx to the alpha squared, yes, is O of log of x to the minus c. Okay, so that was proposition 24. Okay, just so you can always take a look at it. So I have to please add also this condition. And it's not only for x to the alpha here, but also x to the alpha squared. Okay, so what I can do here is just split this thing into proposition on the probability px x alpha squared less or equal than b minus the probability that this thing is equals infinity, but this thing is O of x minus c, so I can put here O, which depends on alpha, but anyway. And now I have this, but I can bound this from the total variation, because what is this? What is, well, this is the probability that this thing belongs to the set of integers such that S min is less or equal than B. Okay, but this is bounded from below by the probability. So that was the part where I defined the total variation, and I wrote a problem. And so using that problem, it is I can bound this by the probability of S min. So I replace this thing by x to the alpha. So I reduced an alpha here and move the square. Less or equal than b minus O of x to the minus c minus the total variation of S min of px in x to the alpha. Well, so S min px in x to the alpha and S min px in x to alpha squared. Okay. Which I can bound from above by the total variation between these two, which by the proposition here is just O of log of minus c. Okay, so the best way of doing this is just bounding using the problem that I stated just before I defined total variation. So I can bound this term by this term by minus the total variation of the probability of x in x to the alpha and the probability of x in x to alpha squared. Okay, so I'm using that again. I'm using that problem that I defined just after I defined total variation, and that problem implies this, and the function I'm using is S min for that problem. But this is bounded by O of log by the proposition here. I keep pointing to that direction, but it is here. So, and this is O of log, which can absorb this O of x to the minus c anyway. So this will be greater or equal than the probability of S min of px x to the n alpha. Oops. Less or equal than b minus O of log of x to the minus c. Okay. But now this is almost event bx. Event bx has exactly this, but plus another thing, which I can bound from above, from below by probability of bx minus O of log of x to the minus c. Okay. So basically what I'm doing is just creating a sequence of steps to prove the claim. Okay. And I'm using over and over proposition, the second part of the proposition, together with the first one. Okay. So I want you to memorize. So we deduce this, but I also comment that you can deduce this thing here. Okay. Whenever this is when x is less or equal than b. It's important. When x is less or equal than b, then you can have something like 1 minus something equals to 0. So we have two things. You have the claim and we have this. You know, so maybe what I would do is I would erase just this upper part here. So we started with some probability of S min of nx tilde being less or equal than b, and I reduced that to removing the tilde, and then now I want to prove that, but then so I reduce. So let me just recall. So we reduce. Computing bounded this from below, reduce proving, let's say proving, just recapitulating, let's see, probability of S min of log of 1x odd equals less or equal than b, this being less or equal to 1 minus O of log of b to minus c. We reduce that, this proving this to proving that the probability of S mean of the variables nx less or equal than b, sorry, this is greater or equal. B greater or equal than 1 minus log of b to minus c. Okay. But we know that the event bx 1 over alpha implies this event, but since bx 1 over alpha implies S mean of nx less or equal than b, this event, we just have to show, that b of x 1 over alpha, the probability of this event is greater or equal than 1 minus O of log of b minus c. Well, we already know that if x is less or equal than b, because that's part of the proposition, but we want to do that for every x, so with a constant which is independent of x. And this comes where we have these two things, okay? So this comes from the following problem, which I will leave you to do. And I will give a hint, so maybe I should put, so maybe erase this thing. But this is just a resuming what we did. So let me write here the problem. The problem is the following. So I have all these things, and this problem is what I mean by a standard technique in probability, which I'm already preparing everything to use this problem anyway. So show the problem. Show that if phi goes from 1 to plus infinity to r, is the function is such that there is some alpha greater than 1, there is some c greater than 0, with phi of x to the alpha greater or equal than phi of x minus O of log of x to the minus c, and phi of x is greater or equal than 1 minus O of log of b to the minus c, log of x to the minus c. This holds if, so this is for all x greater or equal than 1, and this is for 1 less or equal than x less or equal than b, for some b. B greater than 1, let's say this is less. I'm taking log, and I don't want to take log of 1. Then phi of x is greater or equal than 1 minus O, and this O can, there is implicit constant that can depend on c, on alpha, but it doesn't depend on b, of log of b to minus c, for all x greater than 1. So the point is, if you have a certain recursion inequality and you have a base thing, which is, that is for x is small up to a certain bound, you have a certain thing, then this thing can be extended to the whole axis. Okay. So that's the problem. And I will give a hint. You can look on Tao's paper, or you can follow my link, my hint. So use a telescopic sum for the terms phi of x to the alpha to the j minus capital J. So j for, I don't know if j is 0 or 1, maybe it's 1. J for 1 to capital J. Where J is chosen so that x to the alpha minus j is less or equal to b. Okay, so the point is, well, to show the result of the problem for x less or equal to b is obvious. You already have, is x less or equal to b, you have this inequality, you can just bound x by b. So this is true if x is less or equal to b. So you only need to show this for x greater or equal to b. So you start for x greater than b. So you start with an x greater than b, and you take this capital J here, and you do a telescopic sum for these guys, and this would generate, and when you do it, you apply all the time this lower bound here, and you have a certain sum to do, which would be convergent, and that sum will produce a lower bound, the lower bound that you want. Okay? So that's the hint. So this is an induction argument you can do. It says implicit induction argument behind it, but you can just do it with a telescopic sum. Okay, but then we can apply, so we can apply the problem to phi of x equals the probability of px, bx, of the event bx. Okay, because we have all the properties here. We have here, have a bound, we have the thing if it's less or equal to b, and so it's supposed to be 1 over alpha here. Yes. Yeah. So if you apply the problem, you conclude that the probability of b of x of 1 over alpha is greater than or equal to 1 minus O of log of b to the minus c. And this holds for all of x greater than or equal to 1. No restriction whatsoever. No constant here depending on x uniform. But we know that that's all we wanted to show, because from this you can go back and bound this from below by the same thing, and from bounding this from below you can go back and then bound this from below, which is exactly what we wanted. Okay, so from the problem we finish okay. So again, just to finish everything, the whole idea was to apply something like this. Okay, that's the whole point. You have this in mind. You know that this method works. You have this technique. This is a technique that's part of your arsenal. So you want to use this. Okay? What's a smart way of using this? It's by comparing this probability distributions nx and n. So you want to estimate this kind of thing. So you want to estimate these guys here. You don't know how to estimate these guys here. Okay? So what you do is, well, you want to estimate these guys for x and x alpha. X to the alpha, but you don't know. So you use this function first passage to help you in a way of comparing these two numbers. Okay, and when you apply first passage, now you have just numbers below x, and they can be the same. So what's the probability of belonging to one set and the other? That's high. That's measured by the total variation. So you go ahead and measure the total variation, you see the total variation is like O of log B, okay, which is great. So then you can apply this induction argument and we'll do the job, okay. So that's basically it. So the next class we will start proving the proposition 24 based on other stuff and so on until we hit the very core of the argument, and that will be a lot of hard work. Okay, so see you next time.